In this video, I'm going to go over the most common mathematical proof techniques that you probably have already seen in a discrete mathematics or bridge course or introduction to proof course. So in this overview, the intended audience here is students who have already taken a course like that and who are taking a follow-up course that might be an abstract algebra course, topology analysis, something like that, where you're going to be putting these proof techniques into practice. So I'm assuming that you've already seen most or all of the proof techniques that I'm going to be talking about. I'm going to review the basics and show you an example for each technique, but this is not meant to replace a full, complete introduction to proof that you would have seen in one of those courses. It's important to understand that most mathematical statements that you're going to see are implications, which means that they're if-then statements. The if part of the statement is called the hypothesis, and the then part of the statement is called the conclusion. There's also sometimes an implicit quantifier. So if we say, for example, if n is odd, then n squared plus 1 is even, then that's really saying that that's a statement about all integers n, and so that for all integers n, if n is odd, then n squared plus 1 is even. We really should write that quantifier every time, but we often don't for the sake of brevity or when the context of the statement that we're making is understood. We also often see definitions, and when we're writing proofs, it's very important that we understand what the definitions of the terms are. And so I'll just use a made-up word here, fnord. If you know that x is a fnord, then you can use the definition of fnord to learn more about what x is and what its properties are. Now, if you want to prove that y is a fnord, you also need to know the definition of that made-up word here to know what you have to demonstrate to know that y is that thing. And so this goes from concepts about even and odd, prime numbers, square numbers, etc. Make sure that you know what that common agreed upon definition of that term is, because that's going to help you write your proof. So some of the definitions that I'll be using in this video are even, and an integer n is even if it can be written as n equals 2 times a for some integer a. An integer is odd if m equals 2 times b plus 1 for some integer b. And an integer k is divisible by b if k equals q times b for some integer q. Some important consequences of this, for example, is that 0 is even, and that's because 0 equals 2 times 0, and 0 is an integer. So sometimes people debate about whether 0 is even or odd, but 0 is definitely even by this definition. This definition also allows me to state that negative numbers are even, odd, or divisible. So for example, -7 is odd, since -7 is 2 times -4 plus 1, and -4 is an integer. So again, you see here how the definitions help us understand not just facts about individual numbers, but as we're going to see, are going to help us write proofs. Now, the statements that we're going to prove, the important mathematical statements, we call those theorems, right? Not every true mathematical statement is called a theorem, but the important ones, the ones that we use a lot, we call those theorems. And we also have minor theorems that either come before or after a theorem. And a lemma is a minor theorem that's used to prove a more significant theorem. And a corollary, or sometimes pronounced corollary, is a minor theorem that follows directly from a theorem. So we've just proven a big theorem, and a corollary is something that comes directly out of that theorem that we just proved. A lemma is something that is not very important on its own, but helps us prove a big theorem that we want to then use. Okay, so now let's get into the proof techniques. So the most important, most common proof technique is called direct proof. So the way we're going to use this is to start with a let statement that assumes that the hypothesis is true. And we're going to see an example of this here in a second. And then we're going to use known facts, definitions, and other theorems to prove that the conclusion is true. So we're going to start with the hypothesis, we're going to end with the conclusion. And we're going to use this as basically our default proof technique. If we have no other indications that we should do something else, we're going to default to using direct proof. So for example, I might say, if n is odd, then n squared plus 1 is even. So the let statement that we start our proof with would just be to say, let n be an odd integer. Again, there's an implied quantifier here that says that this statement is a statement about all integers, and so odd only makes sense in the context of integers. So we say let n be an odd integer. That's going to be the first sentence of our proof. Now the last sentence of our proof is going to be something like, therefore, n squared plus 1 is even. So when we're using direct proof, it's very easy to write the first sentence and the last sentence. And then of course, the stuff that goes in between is going to vary from proof to proof. So now we go back up to the top and we think to ourselves, what does it mean? What does it tell us to know that n is an odd integer? So here's where those definitions kick in. Since n is odd, and we'll even write that, since n is odd, n equals 2k plus 1 for some integer k. So we're using the definition of odd to learn something more about what we know about n from knowing that it's odd. And now we start working towards that conclusion. Our conclusion talks about n squared plus 1. We've got a formula for n here, so let's use that to see what we can say about n squared plus 1. So we might say now, what's n squared plus 1 doing? Well, n squared plus 1 is 2k plus 1 squared plus 1. Now we do some algebra. That's going to give us 4k squared plus 4k plus 1 plus 1. So that's going to be 4k squared plus 4k plus 2. And I want to know that that's even. Now the definition of even is that your number can be written as 2 times an integer. And so we can factor a 2 out here, 2k squared plus 2k plus 1. And we know that that thing in the brackets is an integer. So we might say, note that 2k squared plus 2k plus 1 is an integer. And that's how we know that n squared plus 1 is even. So that's a simple example of a direct proof, hopefully similar to some things that you've seen before. Another fairly common proof technique is proof by contrapositive. This relies on the fact that the if-then statement, if P then Q, where I'm using P and Q there to stand for statements, to stand for propositions, that is logically equivalent to what we call the contrapositive. So this construction here is called the contrapositive of the original if-then statement. So if not Q, then not P. So that's equivalent, and that's sometimes a useful thing. And so what we do, how we use this, is we use direct proof on the contrapositive. Our new hypothesis is not Q. It's the negation of the old conclusion. And so we start with that new hypothesis, and we work towards our new conclusion, which is not P. And we'll often use this when our if-then statement, our original if-then statement, has some negative statements in it. If it's telling us about things that don't happen, then very often a proof by contrapositive can rearrange it and rewrite it in terms of positive statements about things that do happen, and that can make it a little bit easier for us to work with. So here's an example. Our claim is that if n squared is odd, then n is not divisible by 4. So we see that not there, and we think to ourselves, well, maybe this will be better if I rewrite this in terms of the contrapositive. So n squared is odd, that's my P. N is not divisible by 4, that's my Q. So my contrapositive statement is if not Q, so that would be if n is not divisible by 4, so that's just n is divisible by 4. The negation of being not divisible by 4 is that you are divisible by 4. Then my new conclusion is not P, so that would be n squared is not odd. And hopefully we know from various properties of integers that not odd is the same as even. And so we might even replace that and have this be our statement. So now we're going to prove it using the same direct proof method that we did before. We're going to start with our hypothesis. We're going to say let n be an integer that is divisible by 4. And then we leave a blank space, we skip a few lines, and then we write our therefore statement, which is going to be our conclusion. So therefore, n squared is even. And now we go back towards the top and we use our definitions to understand what do we know now from our definitions. We know that n is divisible by 4, so we might say since n is divisible by 4, n equals 4L for some integer L. Now our conclusion talks about n squared, so we might now think about what do we know about n squared. Well, n squared is 4L quantity squared, which is 16L squared. And we want to think about why that must be even. Well, even means 2 times an integer. So if we can factor a 2 out, which we can, we get 2 times 8L squared. And we note that 8L squared is an integer. And therefore, that's why we know that n squared is even. So this is a proof of the original if-then statement using proof by contrapositive. Another common proof method is proof by cases. So this is when we have a bunch of different cases, one of which must be true. So first of all, we need to understand when that happens. So a common example here would be even and odd. So when we have an integer, we know that that integer must be either even or odd. And so those could be our two cases. We might also think about remainders. So for example, we know that when we divide an integer by 3, the remainder must be 0, 1, or 2. And so those could be our separate cases. Which cases you use are going to depend on the thing that you're trying to prove. But in each of those cases, we have to write a separate proof to show that in each case, the conclusion that we want is true, and therefore in all possible cases, the conclusion must be true. And so this is helpful when we need more information. When we don't know much about what's actually going on, we can consider each possible case and say, that gives me an additional piece of information now that I know that I'm in this case that I can then use to work towards my conclusion. So it's not going to be the first thing that you try, but if you run out of juice and you run out of gas trying to use direct proof or proof by contrapositive, this is something where you can generate additional knowledge that you can use to generate your conclusion. So in this we have if n is odd, then n squared equals 8k plus 1 for some integer k. Now we could start trying to do this with direct proof, but starting with the fact that n is odd is going to, we're going to hit a snag. We're not going to be able to get that 8, and we're not going to really understand where that 8 is coming from. So in this case, we're going to break this up based on the remainder when n is divided by 4. So here's our proof. We let n be an odd integer, and we consider the remainder when n is divided by 4. We have 4 possible remainders. Namely 0, 1, 2, and 3. So we have 4 cases. So case 1, the remainder is 0. Well, in this case, n is equal to 4k for some integer k. But this is even since 4k is equal to 2 times 2k, and 2k is an integer. So that means that this case can't happen. We know that n is odd, which means this is not one of the possible cases. If we go to case 2, where the remainder is 1, well, this case can happen. So in this case, n equals 4k plus 1 for some integer k. And now this looks a lot like the direct proof that we've already talked about. We know something about n now, and we want to know something about n squared. So now we take n squared, which is going to be 4k plus 1 squared. When we square that, we're going to get 16k squared plus 8k plus 1. And we can factor out that 8, we get 2k squared plus k plus 1. And that looks like 8 times an integer plus 1, which has the form 8m plus 1. I know the theorem up here says k, but we already have something called k, so maybe we shouldn't have chosen k. Hindsight's 20/20, but that's okay. Which has the form 8m plus 1 for some integer m. Doesn't matter what integer is, it's 8 times an integer plus 1. Now we've got 2 remaining cases. Case 3, I'll kind of abbreviate here just for the sake of time. So remainder is 2. Similar to case 1, this can't happen. You should include those details, but do that on your own as a practice problem, but this is going to be very similar to case 1. This case can't occur. And then finally, case 4, remainder equals 3. In this case, n is going to be 4l plus 3, and we square that. We get 4l plus 3 squared. That's going to work out to be 16l squared plus 24l plus 9. We can split that 9 up into 8 plus 1. And then we can factor an 8 out of all this stuff, and that will look like 8 times an integer plus 1. So I'm leaving out a couple of the details here, but hopefully you get the idea. Proofs by cases are long, right? Because we have to do separate proofs for each individual case. Now we only have to worry about the cases that can actually happen. We may find that some of the cases that we choose can't actually occur, and there's nothing really to prove in those situations other than that the case can't occur. But in this case, in the cases that can occur, we still need to work towards our conclusion. Now, another proof method that's sometimes used is proof by contradiction. So the idea here is that we suppose that we have a counterexample. We've got our if-then statement, and we suppose that we imagine a scenario where we have something where the hypothesis is true and the conclusion is false. Now that's not what we want, right? We want the if-then statement to be true. We want any situation in which the hypothesis is true to tell us that then the conclusion must be true. So we imagine a scenario where that can't happen, and then we work towards a contradiction. And a contradiction is any obviously false statement. And there's lots of ways that that could be. You could have 1/2 equaling an integer. You could have an integer that is both even and odd at the same time. There's lots of different contradictions that you could come up with. And so one of the reasons why this proof method is sometimes frowned upon is because the goal is nebulous. The goal is unclear. We don't know what we're working towards other than we're working towards something that is obviously false. And so this is sometimes used, especially when you have a conclusion that is a negative statement, right? Because we're going to be assuming that the conclusion is false. And so when we assume that, if our conclusion was already a statement that had the word not in it, then assuming that that's false gives us a new piece of information that will help us work towards that contradiction that we're working towards. So here's an example. If n is divisible by 4, then n squared minus 1 is not divisible by 6. So if we decide to use proof by contradiction here, it's often good form to say that we're doing that right at the start to help the reader of our proof understand what's going on, because the reader is expecting us by default to use direct proof. And so they're expecting the first line of my proof to just talk about the hypothesis. But instead, what I'm going to say is suppose. I'm saying suppose rather than let here because I don't really want this to happen. I'm going to imagine this scenario where I have a contradiction, but I don't actually, at the end of the day, want that to be true. So we're saying suppose. Imagine is what we're saying here. Suppose n is an integer that is divisible by 4, and for which n squared minus 1 is divisible by 6, right? That's the opposite of my conclusion, right? Because my conclusion has the word not in it. So I'm going to say that it is divisible by 6. So my first sentence here has the word and in it, right? Because I'm assuming two things. I'm assuming the hypothesis is true, and I'm assuming that the conclusion is false. I have two pieces of information now. But I can't skip down to the bottom and write my last sentence anymore because I don't know what that last sentence is going to be. I just know that I'm working towards some contradiction. So let's just see what we have to work with. We have two pieces of information. So since n is divisible by 4, n equals 4a for some integer a. And then since n squared minus 1 is divisible by 6, n squared minus 1 is equal to 6b for some integer b. All right, so now we have to try to put these two pieces of information together. We have two equations, and so typically what we're going to want to do now is substitute one equation into the other equation. So the n's that are in this second equation, we can replace them with this statement about n from my first equation. So substituting, we have 4a quantity squared minus 1 equaling 6b. So that's 16a squared minus 1 equals 6b. and we want to somehow get a contradiction, right? We're looking for some false statement. So what we could do is move all of the variables over to one side and move all the things that don't have variables in them to the other side, which means I'm going to subtract 6b from both sides. So I get 16a squared minus 6b, and add the 1 to both sides. So I get 16a squared minus 6b equals 1. But now I can factor a 2 out of this left-hand side. So I get 8a squared minus 3b equals 1. And since 8a squared minus 3b is an integer, this says that 1 is even, because 1 here is equaling 2 times an integer, but we know that 1 is not even, and so that's our contradiction. We didn't know that was going to be our contradiction at the start, but that's what it ended up being. This is a contradiction, which means that this scenario that we were imagining, where we had some integer that made the hypothesis true and the conclusion false, that scenario can't actually occur, because if it did occur, it would lead to 1 being even, and we know that that's not true. All right, finally, and again, if you've seen this before, this is, I'm sure, your favorite proof method, but it does come up and it's worth understanding, is proof by induction. And so this is a very specific proof method that is only used to prove statements about positive integers. And so we break our proof up into 2 possibilities. We've got our base case, which is where we prove p of 1 is true, and our induction step, where we figure out how many cases we've checked. So we let m greater than or equal to 2 be the first case that we haven't checked. So we imagine, for example, maybe we checked the first 5 cases and then got lazy and stopped, and then m would be 6. So m there just stands for whichever case we haven't yet checked. And then once we know that, we prove that that case must be true based on the previous cases. So again, induction is fairly complicated, and I'm not going to reteach it to you in this video. So I'm hoping that you've seen this before at some point. And it should only be used if all of your other proof methods fail. It definitely should not be the first thing that you try, but it is a powerful proof method that can be used in some scenarios. So let's try out proof by induction on this statement. A set with n elements has 2 to the n subsets. So that's going to be our statement that we're going to call p of n. So let p of n be the statement. A set with n elements has 2 to the n subsets. So our base case talks about p of 1. So we're going to let S be a set with 1 element. Say S equals the set containing X. And we want to show that S has 2 to the 1, which is just 2 subsets. Now S has 2 subsets. It does, in fact, have 2 subsets. And we can say what they are. The empty set and S itself, the set containing X. So S has 2 to the first equals 2 subsets. Now for our induction step, we suppose that we've proven this all the way up to some value that we're calling m. So let m greater than or equal to 2 be given, such that p of 1, p of 2, etc., all the way up through p of m minus 1 have all been checked. And now we suppose that we have, maybe we'll call it T, be a set with n elements, sorry, m elements, because we want to prove P of m. So let's give those elements names. So let's call them x1, x2, all the way up through x sub m. Now, how are we going to use the fact that we've checked this for m minus 1 elements? Well, what we're going to do is we're going to temporarily remove one of the elements from T. So let's write, we're running out of letters of the alphabet. Let's call this U, right? U equal just x2 through xm. So we're going to kind of take x1 out of my set and put it aside. Well, our set had m elements, And so that set U has m minus 1 elements. And so U has 2 to the m minus 1 subsets, because we've checked P of m minus 1. P of m minus 1 says something about sets that have m minus 1 elements. U is such a set, so P of m minus 1 tells us something about capital U. Now, because U contains elements in T, any subset of U is a subset of T. Any subset of U is a subset of T. But what's more is I can take each of the subsets of U and put x1 into it, and that will also give me a subset of T. That's also a subset of T. So that means that T has 2 to the m minus 1 plus 2 to the m minus 1, which works out to be 2 to the m subsets. So that means that P of m is true. And these are the two parts of our proof by induction. Now that we know that anytime we've stopped checking, the next thing that we haven't yet checked, that must also be true, you can imagine a line of dominoes where we've knocked over the first domino, and we know that however many dominoes we've knocked over, the next one will fall. That together is why induction works. That proves that the statement is true for all positive integers n. Okay, so in general, there's a lot of information in this video. Feel free to rewind it and watch it over and over again. But what you want to do is model your proofs after proofs that you've seen in class and or your textbook. So don't try to reinvent the wheel. Use examples of proofs that you've seen either in this video or in your class or in examples, other theorems that you've seen proved, and try to model your proof after that. You do want to develop your own style for how you construct your arguments, but you want to err on the side of saying more, not less. So it's always better to say more and have to trim it down than not saying enough and leaving out reasons for why things are true. Focus on writing a convincing argument. Use complete sentences, use explanations rather than just algebra or equations. Use language, use capital letters, period at the end of the sentence, right? Try to get better at writing, not just writing proof, but just writing in general. So hopefully this video was helpful for you. I know it was a bit long, but this is hopefully a good resource for you as you get better at writing proofs in your classes.